Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Welcome to the MIT Faculty Forum. I'm David Corcoran, and I will be your moderator. I'm the Associate Director of the Night Science Journalism Program at MIT. For those of you who have never heard of our program, we bring 10 professional science journalists to MIT for the academic year as research fellows. And they spend the entire year taking classes at MIT, Harvard, and other educational institutions in the Boston area, and doing research projects and taking part in many different kinds of events. I was, for most of my career, I was a science editor at the New York Times. As a reminder, we will welcome your questions during this chat. For MIT alumni joining us using Zoom, please use the Q&A feature found on your toolbar. For all others listening on YouTube, you may add your questions to the comments field. We also encourage you to tweet using the hashtag MITBetterWorld. We'll get to as many questions as we can. Today we hear from a panel of experts who will share some of their current projects and research on extreme weather and superstorms. Let's start with an overview from each panelist. You might catch us up on your career since leaving MIT, then talk about your current projects, and we'll start with Howard Bluestein.
Okay, hello everyone. I'm from the Boston area originally, and my PhD research at MIT involved tropical meteorology. And I came out here to the University of Oklahoma to study tornado. I've been here ever since. I'm just going to show you a little bit about what I've been doing. And let's see if I can get this work. Can you all see my PowerPoint? Okay. I'm going to talk about probing tornadoes and their parent storms using mobile rapid scan Doppler radars. And I'd like to acknowledge the National Science Foundation for support over the years. This is a photograph I took from a helicopter in Moore, Oklahoma several years ago after a major tornado moved on through. So you can be impressed by what a large tornado does. You can see that, I hope you can see, that roughly a 1, 2, 3, 4, 5 block area through Moore was pretty much devastated by this tornado. It was a very, very strong and wide tornado. This is what it looked like at the ground zero. And these are 360 degree, well, 280 degree panoramic pictures. And you can see that virtually everything is wiped out. It's very, very, very sad and to see something like this in real life. But this is what we're trying to get at. We're trying to understand the tornadoes that are spawned that do this terrific damage. The scientific motivation for what we do can be looked at in several broad questions. One is, what's the source of vorticity? That's the source of rotation. It's the curl of the wind field in tornadoes. A second question is, why do tornadoes sometimes form, but most of the time don't form? What's special about the storms that produce tornadoes? Third is, what level do tornadoes form, and how, if at all, do they propagate upward or downward? The tornadoes begin at the ground and work their way up. The tornadoes begin aloft and work their way down. What happens? And finally, what happens when a vortex, like a tornado, interacts with the ground? And there's the rub. You have a vortex rubbing against the ground. And what effect does this have on the tornado? There are a number of different methods of addressing these broad questions. One is you go out and take observations, which is what I do, using mobile Doppler radars. Another is we can use numerical models, especially highly idealized numerical models. And finally, you could take observations and assimilate them in, put them into numerical model to see what happens. There's 3 different things you can do. I focus on the first, but we also have made use of the other 2 to some extent. There's a need for mobile Doppler radars. First of all, we need to get really close and semi-personal with the tornado to maximize the resolution, spatial resolution. The radar beam spreads out as it goes from the radar. So the closer you are, the narrower the beam is. We also want to optimize the number of cases we get. If we stick to a radar that's fixed to the ground, chances are we're going to have to wait an awful long time to get one storm to come to the radar. So we go out to the storms. Also, when you get near a tornado, you can get not only the radar information, but you can get visual observations. You can see what's happening and try to correlate what you actually see with what's happening in on the radar. We need rapid scan radars. These are radars that can scan a whole volume in the order of 10 seconds or less. And the reason is, if you've seen tornado videos, tornadoes evolve very, very quickly on the order of seconds. So if you want to catch the tornado in the act of forming, you need to be able to scan at least once every 10 seconds. Also, sometimes you have more than one radar looking at a tornado, and you'd like to be able to match up the times from the two different radars. And the faster you scan, the more likely it is that you're going to look at the tornado at the exact same time. We also use polarimetric radars, and these are radars that can actually tell us what type of hydrometeors or particles we're looking at in the tornado. We can distinguish between rain, hail, small droplets, biological scatterers, such as insects and birds, and so on. Very importantly, we can locate the debris in the tornadoes. Also, we can locate the strong updrafts in a tornado, and I won't go into that in any great detail, but we're able to do it. There's a picture of our rapid scan radar going around, scans 180 degrees a second. There's a history of our field operations over the last 25 to 30 years. We began in the late 1980s with a portable solid state 1 watt radar, and we've gone up through the last two radars are this one's electronically scanning. This one is rapid scan. There's polarimetric capability. And finally, our group is developing electronically scanning polarimetric Doppler radars. And these are becoming online, not coming online, but we'll be able to test them out hopefully a few years. This is an animation of the formation of a very, very large tornado in El Reno, Oklahoma, several years ago. And you can see that when the tornado develops, that it develops an eye. Let me show you that right in here. And then that's the hook echo and the eye. The inside of where a tornado is, the winds are rotating very quickly, which means that the heavy scatterers like raindrops and debris and flying cows end up centrifuged out. And so we end up with a region where there's just relatively few scatterers, and that's why we see the eye. This is totally different from why we see an eye in a hurricane, but in radar they look the same. We also are able to see small multiple vortices within tornadoes. This is one here. We have the yellow next to green and purple, yellow next to green and purple. We can track that vortex signature, and we found in this particular one that it moved at a speed of 78 meters per second around the parent tornado, and the wind speeds near the ground were about 135 meters per second, which is about 300 miles per hour. Very, very strong wind speeds that we could see on radar. These multiple vortices have a particular type of behavior. We find that the green marks where they begin, the red marks where they end. This is for some very robust, long-lived multiple vortices, again, that are responsible for extreme damage. They seem to form in this left rear quadrant of the tornado and wrap around and dissipate in the front of the tornado. We've also found by looking at the difference in velocity across these vortex signatures, remember whoops, that wasn't supposed to happen. If we have a vortex, the flow is flowing away from the radar on one side, towards the radar on another, away from the radar, the reds toward the radar, the blues and greens and purples. And if we look at the difference between the incoming and outgoing, we have a measure of the strength of the vortex. And what we find here, looking at time on the abscissa going to the right and height going up on the left, we find that we get greens, which we get a strong mesocyclone about 1 kilometer above the ground. Each tick mark here is about 1 minute. So once that low-level mesocyclone appears, About 2 minutes later, the tornado appears at the ground. Tornado begins at the ground, not aloft. And just a few minutes later, that tornado propagates vertically, very, very quickly, within the time it takes us to go from one scan to another. Getting near the end, this is an animation of debris rotating around the large tornado. And here you see debris rotating in a cyclonic manner, counterclockwise manner around the large tornado. There's a second tornado that's moving in a different direction down here, which is rotating in the opposite direction, anticyclonically. So we can actually see cyclonic and anticyclonically rotating pairs of tornadoes. And then finally, we can look at the evolution of debris in a tornado. The red marks an isosurface, which denotes the debris from one of the polarimetric variables that we see in the radar. And this is the top of the radar volume. You can see as we go on, as the tornado dissipates, the debris column becomes narrower and narrower and disappears. But near the ground, it becomes wider and wider and spreads out. So we have a little bit of a problem here. National Weather Service is looking for a debris signature in a tornado, and you find that it's getting bigger and bigger and bigger and bigger. Doesn't necessarily mean the tornado is weakening. It doesn't mean the tornado is getting bigger. It means that it could mean the tornado is weakening and the debris is just settling out. Future and ongoing work, we're going to be using our data in tandem with large eddy simulation models, and we hope to, again, we used this once before, a mobile Doppler LiDAR, which is even better than a radar for looking into a tornado. And that's
Thank
all
you. Thank you very much, Howard Bluestein. Alumni, we're already getting some questions, and please send us more. We'll try to deal with all of them after the panelists have had a chance to give their initial presentations. We move on now to Dr. Allison Wing. She's an assistant professor of Earth, Ocean, and Atmospheric Science at Florida State University. Allison.
Thank you, David. Good to be here with everyone. So as David mentioned, I'm an assistant professor at Florida State University right now. I graduated with my PhD from MIT in 2014 in atmospheric science, where I studied tropical convection. And after that, I went on and had a postdoc at Lamont Area Observatory of Columbia University, where I was a NSF postdoctoral research fellow, and I studied tropical convection there as well as tropical cyclones. And actually one of the people that I worked with as part of my postdoc was Dr. Adam Sobel, who's one of our other panelists here. So it's good to see him again. And then after that postdoc, I started at FSU, where I've been here about a year now. So I'm going to give you just a very brief overview of some of the things that I've been working on over the last couple of years and continue now. So let me pull up this PowerPoint. Okay, so broadly, I study tropical cyclones, meaning hurricanes, typhoons, that they're all the same thing. It's just we call them different things in different parts of the world, but tropical cyclones is the general name. So I study tropical cyclones. I study tropical clouds and convection and climate. And so how climate affects these different phenomena and how these different phenomena affect climate. And so the background image you're seeing here on the screen is Hurricane Irma, which was the recent hurricane we had this past fall in September that impacted the Caribbean and Florida, including a little bit in Tallahassee, where I live. So one of the tools that I use to understand hurricanes is models. And so I'm going to show you a result from a model simulation. And the question that most of my research is focused around is the question of how do hurricanes form? What are the physical mechanisms that cause the clouds to cluster together and rotation to begin and this hurricane to form and intensify? And so there are several different ways you can do this. And as I mentioned, one of the tools I used is a computer model, a numerical model that solves the equations that govern how hurricanes form. And so this is just an example from that. Let me just get it started. So here it's an interesting simulation because this model includes all the complicated physics and processes that controls how hurricanes form, but it's set up in a really simple way. It's simulating an imaginary hurricane, so not a real one that occurred like Hurricane Irma or Katrina, but an imaginary hurricane over an imaginary patch of the tropical ocean. And so here in this animation, where you see white and gray, those are the clouds that you see in the storm. The bluish colors are humid, moist air, and the white colors are dry air. And you can imagine this as we're like floating up in space, looking down on the top. And so I'll get this started here. And you see initially, you kind of have clouds everywhere. And this would what the state would be like in the atmosphere, before a hurricane forms. And they kind of move around all over the place. And I'm going to jump ahead a little bit when things start to get exciting. So now you see kind of in the middle here, there's this large area that's bluer, more humid, moist air. And hurricanes like to form in humid air. And so the clouds start clustering together and it starts spinning rapidly, as you can see here. And so now this kind of looks like a hurricane does from the satellite image I showed earlier. You see the clouds clustered in a tight sort of ring around the center of the rotation, a clear eye, but you also see some spiral bands that go out. And it's really moist and humid near the center of the hurricane and dry around the edges. And so what I do is I go through these simulations in detail and probe all the different processes that are causing this to happen and see what controls exactly when the hurricane forms, how quickly it forms, how intense it gets, and use that to kind of improve our overall theoretical understanding of how hurricanes form. And we'd like to have a better understanding of that because that would then allow us to have improved forecasts for hurricanes, but also have a better understanding of how they might change in a future climate. We know some things about how hurricane strength or intensity might change, but we don't have a good understanding about the number of hurricanes and how that might change in a future climate. And one of the reasons is that we don't really have a theory for what controls from a climate sense how many we get, why we get around 100 every year. And so I'm trying to, by improving our basic theoretical understanding of how hurricanes form, work towards answering that question. Now, a hurricane or a tropical cyclone, you could think of as a very specialized form of a more general type of phenomenon known as organized convection. And so that is the other area of focus of my research. And it's the basic question there that I address are, why do tropical clouds clump together? So this is actually a photograph from the International Space Station of some tropical convective clouds in the Caribbean, actually. And you can see there are several different thunderstorms here that are all kind of clustered together. And this turns out to be quite common in the tropics. You often see these clumps of clouds rather than them being scattered out. And so we want to understand what causes that to happen. And so I again use a combination of theory and observations, but mostly this idealized numerical modeling to help answer this question. And this question, how do tropical clouds clump together? What causes that? That was the focus of my PhD work, and I'm continuing to work on that problem as well. And one of the reasons we'd like to understand that better is because we want to know how this clumping of tropical clouds affects climate, and how does climate affect the clumping? So in a warmer climate, will the clouds clump together more, or will they maybe more scattered out? And this is important because these clusters of clouds, they bring a lot of extreme precipitation to places in the tropics. They control a lot of the cloudiness. They control how humid it is and when it's dry versus moist. And this can mean that they could have an impact on climate. And so I'm organizing a big international project right now to have lots of people come together to run model simulations to try to get at this question. So that's all I'd like to share right now, and I'd be happy to take your questions about that, after the other presentation. Thank you.
We're already getting some great questions, but keep them coming, alumni. Our final panelist is Adam Sobel, PhD 98 from MIT. He's a professor in the Department of Applied Physics and Applied Math in the Department of Earth and Environmental Sciences at Columbia University.
Thanks, David. It's an honor to speak to MIT alumni today. And let's see, I'm going to just share the screen right off the bat. Full screen it. So I just have a brief introduction. We were asked to say a few words about what we've been doing since leaving MIT. So I'm not going to show a lot of research, but I'll just give a description of sort of the trajectory that my career has taken. As David said, I got my PhD from MIT in 1998 in course 12, as I believe all of us did at different times. And I at that time was studying the stratospheric polar vortex with Professor Alan Plum, and that is where the ozone is and where the ozone hole forms. And so that was what I did my thesis on. And then I went as a postdoc to the University of Washington, where my advisor, Chris Bretherton, was also an MIT graduate from some years earlier. And I switched then to studying tropical meteorology, which is what Allison and I have in common. And so we've worked together, as she mentioned. And I've been doing that ever since. I came to Columbia in the year 2000, where I'm jointly appointed in two departments, applied physics and applied mathematics, which is in the engineering school, and earth and environmental sciences, which is in the School of Arts and Sciences and is on a different campus. My research interests, and let's see, okay, there we go. I would say I was trained as an atmospheric dynamicist, somebody who studies the large-scale fluid dynamics of the atmosphere. I think all of us share that. That's an MIT strength. I've been working also on climate, problems of climate variability and climate change, and a lot of what you would call tropical meteorology. As with Allison, a lot of my work has been trying to understand tropical weather and climate phenomena from a sort of fundamental point of view. What makes various phenomena happen? You know, why does it rain here and not there, and why now and not at some other time? That kind of problem. I've been working on hurricanes since about the time I came here, which is about 18 years ago, and so I've been doing that ever since. But in recent years, the theme of extreme weather more generally has engaged me more and more. So hurricanes is still a big focus, but also heavy rain events and severe convection, which is tornadoes and hail. My emphasis here is not on this detailed physics of those storms, as Howie showed, but on how these storms relate to the climate in which they occur. So we try to understand, as the climate changes, whether due to natural or human causes, what kind of changes do we expect in the nature of the extreme events, in their frequency and their intensity and their location, their duration, whatever it might be. And in the last 5 years, really since Hurricane Sandy hit New York City, which I guess now is almost pushing 6 years, I've been doing more applied work in addition to that kind of basic science. So Sandy kind of changed my perspective on life a bit. I was here in New York, and I should say I was born and raised here as well. I've lived most of my life here. And having this massive disaster from a phenomenon which I study happened to the place in which I lived was sort of transformative. And I ended up speaking to the media a lot and thinking a lot about the broader implications. And that's led to some more applied work, including collaboration with the reinsurance industry. And so I wanted to just show one slide of science here. This paper just came out a couple of weeks ago, so I'm kind of excited about it. And this is the title of it and one figure from the paper. So it's an environmentally sourced tropical cyclone hazard model. And so what's shown, let's just say what the figure shows, and then I'll tell you what it means. So the top panel shows 12 or 13 years of hurricane tracks over the whole world. Tropical cyclone and hurricane mean the same thing, one should say. So these are all the tracks color-coded by intensity. So the reds are the really strong ones, category 4 and 5. The blues are the weak ones. And you can see, that they like some certain places. The West Pacific has the most, especially the most strong ones because they're red, and the Atlantic has quite a few, especially ones that make it up to high latitudes. The equator, there's a belt that doesn't have any, and then there's some in the southern hemisphere. The bottom is a model, and I'll say a few words about the model, but let's just see what it is. It's a model that reproduces hurricane tracks. That looks sort of like the observations. You can see that it's by no means perfect. There's too many in the center of the Pacific. There's not enough in the Atlantic. But it's a model world in which there's artificial hurricanes. And the problem it's called the hazard model because the kind of problem this was designed to solve is the following. Let's say we want to know the probability of a category 3 hurricane hitting the MIT campus in Boston, where there's hurricanes are quite rare, and the ones that do come by there are quite weak. So it hasn't actually happened in historical memory that's happened. But so do we believe that it's impossible? And I think the answer is no, we don't believe it's impossible. We just believe it's very unlikely. But if we don't have data to say how often it's happened, then how do we know what the probability is? We have to use some sort of physics. And what this model does is it generates artificial hurricanes in a way that's both computationally inexpensive, but that incorporates some information about what the state of the climate is. So this is not a climate model. It doesn't simulate the whole behavior of the atmosphere and ocean on first principles. Rather, it takes information from either observations or from some other representation of the climate, which could be from a climate model, and it generates storms through an algorithm that combines some knowledge of physics with some knowledge of the statistics of past storms to generate artificial hurricanes that are consistent with the climate. And if the climate changes due to natural or anthropogenic reasons, we can see how the cyclones change. And because it's computationally inexpensive, we can generate lots and lots of cyclones. We can generate millions of years, if we want, of artificial histories. And that gives us a plausible way to represent the probabilities of rare events. So this is very important for any application where you want to know what your risk is of an event that's low probability but high impact, like a Category 3 hitting Cambridge, Mass. And so we developed this for academic purposes. We want to understand hurricane risk in the present and past and future climate. But the reinsurance industry, which has to estimate the risk of rare events, is very interested in this, and we talked with them a lot. And they really pioneered this kind of modeling. The first people to do this were people in reinsurance who developed models like this starting in the 80s and especially more into the 90s after Hurricane Andrew, when they realized that they needed to estimate risk better. But that their models are really just based on looking at past hurricane tracks and generating more that look like that without knowing really anything much about the climate. Then Kerry Emanuel, an MIT professor who's Allison's thesis advisor and also one of my teachers when I was there, developed a model of this type that I'm showing here. As far as I know, his was the first model of this type that incorporated climate information. And I won't explain how his model works, but it's very brilliant. And it is what gave me the idea and inspired me that this is an important kind of work to be doing. And we developed our own model because we thought there ought to be more than one model that is able to generate synthetic hurricanes cheaply, to do risk assessment, that knows about climate. And ours has the further attribute that pretty soon we'll make it open source that anybody in the world can use it. So the paper we've been working on this for several years, developing this. We had to solve a lot of problems, and I'm not explaining to you really how it works. If anybody has questions, I'd be happy to explain it. But I just this just came out a couple weeks ago, so I'm excited about it, and it gives a sense of the kind of things I'll be involved in. So just for the last slide, I wanted to put up some contact information. I have been somewhat more publicly engaged in the last few years than I was in the earlier part of my career. I wrote a book about Sandy, which has some of the science as well as some of the larger ramifications as I see them, and web URLs and Twitter handles and stuff like that. So that's all I have. Thanks.
Well, thank you very much, Adam Sobel. We're getting a lot of questions about climate change, and so I just want to pose a couple of general questions to all the panelists. Karen asks, how much have you seen climate change in the areas you study, and explain what changes you've seen over the years and how you figure out what things are due to. And then I want to narrow that question down a bit. Another alumnus is asking, what about the cold weather in the Northeast this year? What is that all about? Anybody?
Well, I guess I should say something about the question of climate change and what how much we see it. I guess maybe we can take for granted with this audience that climate change itself is a real thing, and on the large scale, it's quite evident in very large scale measures like the average surface temperature of the planet. That we see that going up very clearly, and you can't explain it without a human influence. But I think the question is about, and it's a much more challenging question, is about extreme weather events. And as we look at these, whether it be tornadoes or hurricanes or snowstorms for that matter, as we see extreme ones come and go, and people ask, what did this have to do with climate change? That question is, when it comes to an individual event, that the name for that is attribution. So that you're attributing it to causes. And the National Academy of Sciences put out a report about this extreme weather event attribution to climate change in early 2016. I was on the committee that produced that report. So it's not original research. These reports assess the state of the science. So I don't actually do attribution. but as a consequence of serving on that committee, I learned a lot about it. So what you can say is that for the, I think the other, our other two panelists would probably not disagree with this. For these kinds of extreme events, tornadoes and hurricanes, the attribution is still in its infancy at best. It's very difficult still to do attribution on these kind of events. For heat waves, we can do it much more clearly. We can see the signal of climate change and heat waves quite clearly already. For some other kinds of events like extreme rain events, we can see it quite clearly. And what I mean by quite clearly is you can see the statistics of them changing. You can see that they're more frequent or more intense or something, you know, in the observations, as well as that's what models predict should happen. And we have a theoretical understanding of the mechanism behind it. When it comes to hurricanes and tornadoes, I think at least one and sometimes more of those things are not true. So in the case of hurricanes, although we believe we have a lot of evidence that suggests how hurricanes should change with climate, it's still a lot of debate on to what extent we can see those changes yet. And a lot of that is the problem of just that there aren't that many each year. And so you're trying to see small changes in a statistical signal that's, there aren't that many statistics. The statistics aren't that good. So that's part of the reason, but there are other reasons. I would guess that, or it's more than a guess. My impression for tornadoes is that we don't even have a clear agreement among scientists of what should happen to them in a changed climate. And so it's very much, even that much more, you know, far away for us to be doing attribution on individual events.
So let me just follow up, Adam, and ask you, as the only panelist representing a Northeastern university, what about this this weather we've been having, sub-zero temperatures and blizzards in New England and so on?
Right. Well, the first thing one has to say is that it's, of course, not evidence against the occurrence of climate change, because we expect random variability of weather, and at any given moment, that variability, especially in a place like the Northeast, is much larger than the climate change signal. So the weather on a given day is determined primarily by the fluctuations of the jet stream and the high and low pressure systems that come and go, and global warming at most pushes the statistics slightly in one direction. So winter is not extinct. We don't expect it to be extinct. There's no inconsistency with the notion that the climate is getting warmer. That said, there is now a countervailing idea that has been out for a few years that paradoxically and counterintuitively, in the warmer climate, we should have more of these cold events or more severe ones, because the jet stream is getting wobblier as a consequence of the Arctic warming more than the lower latitudes. Now, the last part of that is definitely true. The Arctic is definitely warming more rapidly than lower latitudes, but the notion that that is making the jet stream wobblier and therefore making these kind of events more frequent or more likely is very strongly contested. I am not convinced myself by it. I think the evidence is still not that strong. And if you look across the hemisphere in the higher latitudes, the frequency and severity of cold events is clearly decreasing, not increasing. So that's very much a subject of active debate.
Okay. A question for Howard Bluestein. The alumni says that slide you showed of the tornado damage in Oklahoma was pretty scary. Are we doing anything, or have you learned anything during your study of tornadoes that would help protect communities and people better from tornadoes?
Well, it can't protect people who are in the path of a tornado from not getting hit by it. So the two things that we can do. One is, if we know more about why tornadoes form in some storms and not in others, then we can improve our warnings. So the idea is that we want to give people enough lead time so that if a tornado is coming toward them, that they have enough time either to get out of the way of the path of the tornado or to take shelter. And the second is, if we understand what the wind speeds are in tornadoes and how the wind speeds vary in the vertical, then hopefully structural engineers can design buildings that can withstand the force of a tornado.
I have questions from two different alumni for two different panelists, but on a very similar topic. Heidi asks Howard Bluestein, what about creating mini tornadoes in the lab to study them? And another alum whose name I don't see at the moment asked about creating synthetic hurricanes. So Allison, why don't we start with you? Is there such a thing as a synthetic hurricane? And if so, how do you create it?
Well, if you mean an actual physical hurricane that you somehow create a small version of in a experimental lab setting, as far as I know of, that does not exist, or for tornadoes either. You of course can, generate strong winds in a lab setting and see how that affects things. But for us to study these atmospheric phenomena, our labs are mostly computer models, and so we generate synthetic tornadoes and synthetic hurricanes inside our computer models, inside lines and lines of codes and many numbers. And they're our lab in order to study them. And just like in a lab, how you want to have a control setting and then change different parameters one by one, we do that in our models as well. And they're really useful tools for us because you can do things in a model, in a numerical model, that you can't do to the real world. You can turn off a process like rain or something like that and say, okay, if I turn that process off, how does that affect how the hurricane forms, which we obviously is way more difficult to do in the real world. So they're great tools for us, but at least Howie can correct me if I'm wrong. I don't think that people have generated, you can generate a wind vortex certainly in a lab setting, but I don't think people have been able to generate a tornado in the same way it forms in the real world.
Yeah.
And hey, yes, Howard, what about synthetic tornadoes or mini tornadoes?
Yes, for many years, actually, beginning maybe 30, 40, 50, maybe 60 years ago, people started making miniature tornadoes, but they're not really tornadoes. They're, as Allison said, they're strong vortices that interact with the ground. And you can control various aspects of the vortex. And these experiments, these so-called tornado chambers, vortex chambers, have taught us an awful lot about tornadoes. For example, from the experiments done with these tornado chambers, we know why sometimes you get one tornado, where at other times the tornado breaks up into smaller tornadoes rotating around the main tornado. So those have been very, very instructive. More recently, beginning maybe 30 years ago, people began to do simulations of the tornado models. And by doing so, as Allison said, you can control certain variables and make the tornadoes have different characteristics. So we've learned an awful lot about the structure of tornadoes just from these miniature tornadoes. But you have to think about these laboratory tornadoes or virtual laboratory tornadoes in the same way you think of how a thumb operates. You can model the thumb, but unless you can model the hand and the wrist and all the nerve endings going up to the brain, you really don't totally understand why it forms. We're getting to the point now where the models have high enough spatial resolution that we will soon be able to model tornadoes and their parent storms at the same time. Right now, we're just at the threshold where we're able to model the storm and just barely get down to the spatial resolution that we can actually model the tornado. But even if we were able to have a computer that was powerful enough to model both the parent storm and the tornado, there are physical processes involved, in particular, the turbulence that occurs right near the ground where the vortex interacts with the ground. And we still have problems in making realistic simulations of what happens in the boundary layer where the model actually rubs right against the ground. So we have a long way to go. But yes, it is insightful. Miniature tornadoes in the lab have been very, very valuable, but they're not real tornadoes.
Bob has a Florida-specific question for Allison. Have you had to struggle with the Florida governor's proclamation that, as Bob puts it, dismissing the reality of climate change, and how best to address this kind of political pressure?
And so I myself personally have not been affected by that. I think for the most part, the Florida government doesn't get involved in what its professors at its universities are studying and how they study it, as it should be. It is sometimes frustrating as a scientist who, you know, is aware of the realities of climate change, to see our elected officials dismiss those and not, you know, take them seriously and put effort to them, especially when Florida is a state that is at risk from so many different types of weather phenomena and impacts of climate change, from, you know, sea level rise to hurricanes and so on and so forth. I personally have not yet in my career engaged in science policy discussions. I have so far stuck to just trying to answer the questions about hurricanes, but, you know, as everyone who's an informed citizen about these issues, you know, it's up to all of us to kind of communicate, you know, that it's an important issue and that it's something our politicians should take seriously.
Adam, Abigail asks, have you engaged with folks interested in climate resilience as a result of your work? And if so, are there approaches you think may be particularly promising?
Let's see. So, I mean, I guess it depends what you mean by engage with. I mean, the outside partners that I talk to the most who are involved in this are the reinsurance companies whose interest is in, you know, in selling reinsurance, but who also have some interest in resilience, because in the long term, you know, they understand that it's not just about insurance, it's about helping the society be more prepared. And there are some socially responsible people in that industry. I have gotten to know quite a few people in New York City government who are involved in trying to improve the resilience of the city post-Sandy. So there's our, what used to be called Plan YC under Mayor Bloomberg, and now under de Blasio is split into two agencies called, and the one that deals with resilience is called the Office of Resilience and Recovery, headed by a guy named Dan Zerilli. I don't have any formal role with that agency, but I know them and we talk to them. And then we have been starting to develop some collaborative work at a sort of informal level with the Office of Emergency Management in New York City, who are the people that, rather than sort of developing the infrastructure, their role is more in really dealing with the emergencies once they happen, but they have a planning role as well. So I talk to those people. The questions they ask have some influence in how our, you know, the research agenda of my colleagues and I develop. We've recently been working on a project in the city of Mumbai. It's a long story how we got involved in that, but asking the question, could a Sandy-like event happen there? The answer is yes, with low probability, but very high consequences. Those are the kind of events we're interested in studying. In terms of what approaches are best, I don't think there's any unique answer to that. It really depends where you are and what kind of place you're in. And by the way, this goes not only for what we call resilience, which means just your ability to bounce back from a bad event, but also adaptation, which is the word used in the climate change context to mean adapting to changing conditions. When it comes to extreme weather events, really they're not that different, in the sense that extreme weather events, even without climate change, can cause a lot of damage. And often the biggest ones we are unprepared for, precisely because they're rare, they haven't occurred in a long time. And so, you know, cities and human infrastructures aren't built with them in mind, because they happen so infrequently that nobody remembers the last time one has happened. Climate change is changing the probabilities over time, but in some sense, so imperceptibly that when it comes to the rare events, they happen so infrequently anyway that it's hard to perceive those changes in risk, even if they're there on short time scale. So it's sort of the same problem of being prepared for extreme events. And I think there's no single answer to that. If you're talking about, should New York City build a seawall around it, or, you know, what's the best way to respond to tornadoes in Oklahoma City, or the prospects of severe drought in California, you know, the measures are obviously place specific, and they depend not just on the climate context, but also on the properties of the human society within it. I think the one thing you can say, if we think about the climate change issue, is that all adaptation is local, and while mitigation is global, in the sense that, you know, everybody emitting a ton of CO2 into the atmosphere, it's all the same. I mean, it all gets mixed up very quickly, and whether we do it or somebody in China does it, it all affects climate in the same way. And that's why, you know, negotiations to reduce global warming are global. Everybody has an equal role proportional to the amount of, I mean, the amount of you can reduce your emissions is how much emissions you had to begin with, but I mean, it's all the same. Whereas adaptation is all about each individual place. And the other thing is, if I take a ton of carbon out of the atmosphere, it benefits everybody. Whereas if I build a seawall around myself, it only benefits me. So on the one hand, that gives it means the political motivation for any given elected official to do adaptation is much greater in some sense than for them to do mitigation, because adaptation they might get some recognition for right away, or although even that's not true sometimes, because if they're building a protection against an extreme event, the event might not happen, and they don't get credit for it, until they're out of office. But mitigation is even more diffuse. I mean, the credit for that is even more diffuse. So there's no general statement I can make about what are the best resilience measures, and really one should do cost-benefit analyses in any given situation, as well as worrying about the political context and all that. But what you can say is that the political and economic incentives for resilience and mitigation are very different from those of climate change mitigation.
Well, let me follow up on that. How do you feel about geoengineering approaches to mitigating climate change?
So let's first be specific. I mean, geoengineering means anything we do to engineer the Earth system. I take it you mean solar radiation management, where you shoot dust into the stratosphere to block the sun. Is that what we're talking about?
Well, that's certainly one thing that has been suggested.
Well, another form of geoengineering is carbon capture and storage, which is pulling carbon out of the atmosphere and that, I don't think anybody has any problem with that. If we could do it in an energy efficient way, so that economically was feasible, which it isn't yet, but maybe the technology will be there someday, I don't think anybody would have any ethical problem with that. Whereas the geoengineering where we shoot tiny bits of dust or aerosol into the stratosphere to reduce the amount of sunlight coming in, to cool the climate and thus compensate for global warming due to greenhouse gases, which operates in the infrared part of the spectrum instead of the visible. So we're sort of, it's keeping energy out to balance energy that's coming in two different parts of the spectrum. So you can see from that they're not canceling each other exactly. Sunlight is not the same as infrared radiation. That many of us have much greater difficulty with that, because first of all, it's a general truism that in environmental issues, that if you cause an environmental problem, it's usually not a good idea to aggressively engineer the system in some other way to reduce it. It's better to stop doing the thing you're doing, because there's always unintended consequences. The geoengineering solar radiation management is no different, in the sense that although it would cool the climate, we know it would work, and it's not that expensive on the big picture, all things considered, but it has a lot of other negative effects. It would change the circulation and precipitation patterns on the Earth. It wouldn't stop the acidification of the oceans. And perhaps most importantly, it's very quickly reversible. So you have to keep doing it. The dust would wash out of the idea is you're shooting dust high up in the atmosphere. It might stay there for a year or two, but it's going to wash out after that long. Then you have to do it again. So you sort of become addicted to it. And you have to keep doing it. And if you ever stop doing it, then the climate would warm right up again. So it could instill a sort of sense of complacency. The third thing dangerous about it is that unlike emissions reduction, any one country with reasonable means could do it. Many of the countries on the Earth have enough resources to do this independently. So unlike emissions reductions, which everybody has to agree upon, everybody would have to agree not to do it in some sense at some point. In other words, any one country could take it upon themselves, and the results might be better for some countries than others, or might be perceived to be better for some countries than others. You can imagine starting wars. So on the one hand, we don't seem to be taking any other aggressive action, and for those of us who are really concerned about the climate problem, geoengineering starts to sound more and more like maybe we ought to be thinking about it, because at least we know it would work, and nothing else we're doing seems to be working politically. At the same time, it raises a lot of grave concerns, and so I think that's the source of the ongoing debate among scientists and policy people that is really more of an ethical and political debate than it is a scientific one.
Allison, I have a couple of hurricane questions for you. One, Cynthia asks, are there much fewer hurricanes in the southern hemisphere as opposed to the northern hemisphere? And if so, why? And another alum asks, do most hurricanes form off the coast of Africa? And if so, why?
So yes, there are in total fewer hurricanes in the southern hemisphere than the northern hemisphere, and that's mostly because If you noticed on the plots that Adam showed in his slide, there weren't any hurricanes really at all in the South Atlantic and in the Southeast Pacific. And that's because you need particular environmental conditions necessary to form hurricanes. You need warm ocean temperatures, you need humid air, you need low wind shear, so the wind can't change too much vertically in the atmosphere. And those sorts of conditions are unfavorable in those particular ocean basins. The Southeast Pacific has pretty cold waters. That's the cold tongue, it's called. And the South Atlantic has pretty high values of wind shear. And so I think there have been maybe in our history a handful of hurricanes that have formed there, but in general, it's just not a favorable environment. So that's why you don't see them down there. As for hurricanes forming off the coast of Africa, so hurricanes in the North Atlantic, many of them form from what's called African easterly waves, which are tropical disturbances, clusters of convection and thunderstorms that form on the African continent and move with the prevailing winds into the Atlantic Ocean. And hurricanes like to form from a pre-existing disturbance. So having that initial cluster of thunderstorms combined with favorable conditions is the sort of ingredients you need for a hurricane to form. And so once those clusters of thunderstorms move over the ocean where the conditions are favorable and there's that ample source of energy from the fluxes of heat from the sea surface, then some of them, if the conditions are right, can form hurricanes. But tropical cyclones can form from many other mechanisms as well. Just from any sort of thing that organizes convection gives you a sort of initial little circulation. And so in different parts of the world, they form from different things. And even within Atlantic, some of them, they don't all form from that, but many of them do.
We're running low on time here, and I'd like to ask each one of you briefly to answer this question, starting with Howard. What kinds of extreme weather events do you think we can look forward to in the next, let's say 5 years?
I can't answer that. I can try to address tornadoes, and the answer is I don't have the vaguest idea what's going to happen. I can't predict what's going to happen 2 weeks from now, and I'm not going to be able to predict what's going to happen over the next 5 years. In order to get tornadoes, we need strong tornadoes. We need supercells. We need the conditions to be right for supercells. We need strong vertical wind shear, and that depends upon how the jet stream is configured. And simply cannot predict that at all.
Adam.
Sorry, I couldn't hear who you were calling on there. Is it me?
That was you.
Sorry.
Yeah, look ahead for us.
Yeah, I mean, my answer is 75% the same as Howie's. I mean, in the sense that the specific events we can't predict any further than a week or two. That's as far as our forecast models go. Beyond that, we can only talk about probabilities. And by and large, the probabilities, there are some predictable signals based on things like El Nino. But that'll even, at best, even goes out a few months or maybe, in the most extreme case, maybe we might have some information pushing a year in advance. But on the 5-year time scale, we really don't have any predictive skill, except in as much as the anthropogenic component goes. So we can predict with confidence that we are going to continue to see heat waves at a rate and with an intensity in the next 5 years that will exceed the long-term historical average, because we're not going to go back to the temperatures of the 1940s in the next 5 years. We're going to stay somewhere up near where we are with some little fluctuations. So when it comes to the kind of extreme events we're talking about today, mostly because of our research interests, hurricanes and tornadoes, my answer is the same as Howie's. I mean, we can't predict them very far out, and the statistics of them are going to be, apart from signals like El Nino, which move things around a little bit, but they're, or sometimes more than a little bit, but only for a few months. The statistics are going to be hard to distinguish from those of the long-term mean, except for events that are closely related to temperature. And that's mostly heat waves and to some extent heavy rain events, which are more closely related to temperature than you might think. But for hurricanes and tornadoes, really, there's nothing we can say on a 5-year time scale, and if we could, we would be very rich.
And Allison down there in Hurricane Alley.
I mean, I think the most basic thing we could say is that these extreme events, which have been occurring throughout our history, will continue to occur. We're going to keep having tornadoes and hurricanes and heat waves and floods and droughts and also cold snaps and blizzards. I agree with the other panelists that on that 5-year time horizon, there's not a lot we can say with great certainty, with regards to if we should, are going to have more or less or more intense or weaker of a given phenomena. I mean, certainly we have expectations about how some of them might change with long-term warming, but even a 5-year timescale is a pretty short window, and there's lots of natural variability that can oppose that sort of influence on that timescale. But I think like I said, we're going to have extreme weather one way or the other, and have to be prepared for it regardless.
We are out of time. On behalf of the Alumni Association, I want to thank all the alumni for tuning into this faculty forum online, and to our 3 great alumni panelists from the University of Oklahoma, Florida State, and Columbia, and of course, ultimately from MIT. An alum asked, will we be able to see this presentation online? And the answer is yes. In about a week, it will be posted on our YouTube station. Just look for MIT Faculty Forum Online. We didn't get to all the questions you submitted, but we will forward all questions to the panel. Tweet about today's chat using the hashtag MITBetterWorld, and send follow-up questions or feedback to this address, alumnilearn@mit.edu. I'm David Corcoran. Thanks again for watching.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.